The first example today is about drug doses. So let's read this together. Let's x of t denote the amount of a drug in the bloodstream at time t. It is observed experimentally that the rate of absorption, so the rate of absorption, that's going to be the change of x of t. Yes. Rate of absorption, that's going to be dx dt. Yeah, rate of change with time. That's what a derivative tracks. How much the quantity is changing with respect to the other variable. So you're told that it's proportional to the amount of drug present at time t. Amount of drug, that's x of t. So we're just going to write this empirical or experimental law. The rate of change, dx dt, is proportional, so I'm going to call k, or in fact minus k, is more convenient, the constant of proportionality. I'm writing it as minus k, so I can take k positive, because x, you expect the amount of drug to decrease in the bloodstream as it is absorbed by the body, I guess. So if it's decreasing, it means the derivative must be negative. So if I put k positive, then with a minus, I do get a decrease. Okay, well, that's it. We know how to solve this. Yeah, we could do separation variables, we could do integrating factor method. We just write it directly because we remember it now, that the solution is going to be x0 exponential minus kt. Well, that was easy. Typically, we're going to have exponential decay, going to look like this, rapid decay, and then slow tapering towards 0. Starts at x0 and then decays. So if you are a doctor and you want the drugs to be in the bloodstream for a long time, so it can make an effect. It can have an effect. You want to beat this. So what you want to do is you want to bring in boosters. That's how it's called. So you measure K experimentally, and then you realize that after a certain time it's just below some threshold that's making the drug ineffective, and then you boost it again. That's why I'm writing in the next slide. Suppose that the patient is repeatedly given the same dose x0 at regular intervals. All right, so it's going to look like this. If I do a line, like this, x of t. So remember, that's the amount of drug in the bloodstream. I start at x0, it decays, and then at time capital T, I give it again x0. So it's going to shoot up, go above x0, and then it's going to decay again. At time 2t, I repeat, and so on and so forth. That's typically what happens when you have a chemotherapy. You could be spending all afternoon getting those doses. Can we model this mathematically? Yeah. What is the long-term amount of drug in the system? So let's just say after n periods of time, what will it stabilize? Will it just be infinity? Until you can't take no more, right? There's other things that come into action, of course. You need a good mathematician to predict all this, or I guess a good piece of software. So it's a very simplified model, but we could try and make progress. 2t, yeah. So for instance, we know that in the first period here, that's going to behave at x0 exponential minus kt. Right, that's this curve here. And then it's interrupted. And then it's the same curve, but it starts at a higher level. It's going to start at now x of t, but it's going to decay just the same. Then that one is going to behave as x of 2t, right? Because the initial point here, the initial value is x of t, which is going to be this little value here plus x0. We can actually compute all those quantities. Yeah, if I call t minus and t plus the time just before the booster and the time just after the booster, I can write all this mathematically now. T minus, t plus, just before the second dose, and t plus the time just after the second dose. So now I know what x of t minus is. x0 kt, by capital T, that's how much time has elapsed until I get here. So that's my amount. Exponential cap minus kt, that's just a number, so I'm just going to call it r. It's going to prove handy later, where r, that's just for convenience. Yeah, and you can see that r is less than 1, right? An exponential negative quantity is less than 1. Exponential of 0 is 1, and then it just decays. Okay. So I'm just going to rewrite this. X at t minus is r x0, or x0r. Sorry. Keep the same order, x0r. And then x at t plus, just after the second dose, just here now, on this side, I'm starting here. I have this quantity here, x of t minus plus x0. Plus x0, because I've given a booster of the same amount. So I can factorize this, 1 plus r x0. And you see where this is going? I'm going to do the same here at 2t, 3t, and then I'm going to see a pattern. I'm going to go back to leaving cert. Find the series, find the sum. Yeah, good old leaving cert. So let's do that. X at 2t minus. What's it going to be? I've just decayed with the exponential minus kt over that period of time, right? From t to 2t. So it's going to be the initial one, x at t plus, with the decay, which is exponential minus kt. And I have that above there. One plus r x0. And then that exponential, that number here, I've called it r. Okay. And then at 2t plus, If I'm on the other side, I've just given a booster again, so I have to add x0. It's going to be 1 plus r x0r x0, and so on and so forth. And here I see I can factorize by x0. It's going to be factor of 1 plus 1 times r plus r times r. Oh, yes, now I see it. Yeah? Now you see it. Now you don't. Now you see it. Yeah? If I keep going, I can do it at 3t minus, 3t plus. You get the drift. X at n t plus, it's going to be x0, 1 plus r squared, rn. Yeah! Geometric series. That's somewhere. Page 22 in the logbook. There it is. The sum is going to be x0 times 1 minus r to the next power, 1 minus r. Remembering that r is less than 1. And now I can do the limit. Where does this go? As n goes to infinity, that doesn't depend on n. The only part that depends on n is this. But r is less than 1, so it's going to go to 0. So I'll be left with x0, 1 over 1 minus r. The limit xs so you can't go above that level, no matter how many boosters you give. And that's called the saturation level. That would be the long-term level of the drug in the system. Build up over many doses. All right, so now you can play on this. You can talk with the doctor, the consultant, figure out which is the optimal level in the bloodstream for the drug to be effective. Maybe you could play on capital T, you know, the period elapsing between each boosters. Maybe you could play on K. Maybe there's ways to make the decay slower in the blood or faster and so on and so forth. Very interesting, don't you think? Very basic maths, but like you said, you could complicate it very easily with other interactions. Maybe there's a cocktail of drugs, so then you need to couple all those equations, all those differential equations. Maybe there's a reaction from the body, from the immune system, that will counter the effect of the drugs. You could go into this, into a complicated math very easy. But it's very interesting, very prominent topic of research in applied mathematics. Drug delivery. It's called reaction diffusion equations. You'll see more of it in second year and third year. Mostly second year. So that was a nice example of application. Any questions? Did you follow? Is it all okay? I thought it was okay. Radioactive decay. Yes, that's good. Another example of application. So radioactive decay, that comes up often in exams as a short question. Because there's only so much you can ask. And it's also in the book. We'll understand soon now what those words mean. Where is it? On page... No. Huh. seem to find it anymore. Oh yeah, here it is, page 63. In fact, if you have an old version of the book like mine, yeah, there's a mistake on that page. You have the brown version, I hope. Yeah. It's been corrected since. That's the one. That's good. Don't freak out. You're here to count the number of people, right? Let's say numbers out loud to mess them up. 53, 72, 24. It's done? Ah. All done, all set. Okay. So, did you receive an email telling you the course is going to be assessed, that you're going to be able to give feedback? No, not yet? I'll do it tomorrow anyway. Let's just read this. Number of radioactive atoms in the material with half-life of T. So yeah, let's find out what that means. Activity, radioactive decay, half-life. The rate of decay is proportional to x of t. So you just told this. It's true by and large. You can find it experimentally that the rate of decay is proportional to x of t. So let me see. So we're just going to write that rate of decay. So that's going to be the rate of change of the quantity x, and it's proportional. So here it's traditional to call the proportionality constant lambda. Since it's decaying, I'm going to put minus lambda to make it obvious that it's going down, keeping lambda positive. Well, that's it. That's the law. I know how to solve it. That's like Malthus' law. I know that x of t is going to be x0, the quantity at the original time, exponential minus lambda t. So the half-life, there was this word introduced earlier that I used once in a maths movie quiz, if you remember. It's just what you think it is. It's how long it takes for the quantity to be half of what it was at the beginning. Yeah, it's t. Half-life is in time, period of time, such that x at capital T is 1/2 of x0. How long it takes to be halved. We could just compute it from there. It should be x0 exponential minus lambda capital T. So if I solve this equation, I can divide across by x0. I'm left with 1/2 equals exponential minus lambda t. Then I take the log on both sides, or solve it any which way. And then log of 1/2, that's log of 2 to the power minus 1. So that's minus log of 2 divided by lambda. And I get t equals, divided by minus lambda, t equals lambda 2, no, log of 2 over lambda. And conversely, lambda log of 2 over t. That's it. That's all there is to it. And then you look in the tables, and I think there's some of these in the book. Maybe not. I thought so. No, then that's electricity. Oh, maybe here. Half-life. Oh, yeah. Anyway, I'm just giving them to you here. So if you take capital T to be in years, then lambda, you can see lambda is proportional to 1 over T, so it's going to be in years minus 1, and you could just compute one once you know the other, just using those formulas. So let's compute lambda for carbon 14. You told the half-life is 5,568 years. So that's nice if you want to do prehistory, for instance. That's a good element to track, right? If you want to do things in a human life, probably what's PB? Lead is better. Yeah. If you want to do things in the Christian area, radium is better. If you want to do age, I guess at the planetary scale, universe scale, uranium is better. Which is scary when you think that's what we use in nuclear power plants. Okay, let's do this then. If T is 5,000, then lambda is going to be log of T, log of 2. So be careful. Go on now. Yeah. I get 1. Do you get the same? 1.24. That's another 4, yeah. 10 to the power minus 4. So that's with 3 significant digits. Do you get this? Okay. Well, let's do it. Let's do an example. Yeah?
The lambda for PB, it keeps showing up as 0.0.
All right. Maybe there is a mistake. Lambda for PB, so log of 2 divided by 22. Oh, that's good. Oh, yeah. I got 0, 0. Ooh. Thanks. So I should say 3.15 10 to minus 2. I must correct that. Thanks. Well, let's check them all then. Log of 2. I'm doing radium now. Yeah, that's what I get. And then uranium. .5 to the power 10 to the power 9. There's a shortcut for that. Oh yeah, that's at the bottom. 10 to the power 9. I get 1 point. Yes, so that's good. Is it consistent with the book? Let's go totally forensic on this. PB, that's lead, le plomb in French. So that will be at the end. 1, oh, doesn't even do it. Can't find it now. PD, that's not it. Mercury, no. PB, 210. Oh, they don't have it. They have 27, 206, 207, 208. Okay. Radium. Okay, I'm bored now. You guys can check. We can do that at home. Let's do an exercise. CO2 in the atmosphere So that's carbon dioxide is continually bombarded by cosmic rays. This results in the production of carbon-14, a radioactive isotope, which is then absorbed by plants. When the plant dies, all right, no, yeah, makes sense, and the concentration decays. So by comparing a sample material with a living sample of the same material, we're able to estimate its age. Clever! So let's do this. Yes, sorry, if you look, I forgot to tell you, if you look in the blue book, you will see that on page 62 they made a mistake. They have a minus sign. They say activity is A equals minus dn over dt, and then lower radioactive decay is A equals minus lambda n. And so they wouldn't have the minus sign. What do you have? No, on page 62. 63. Hopefully that is right now. Yes, they corrected it.
Oh, so this one's wrong.
Mine is wrong. Yours is right. By the brown book, not the blue book. So, according to the brown book, you could put the two together. It would be n instead of x. Yeah, let's do it with n then. You could put the two lines together to arrive at this law. And then you can solve it, and then you can answer the question. Yeah, n of t, n0 exponential minus lambda t. In case you've forgotten. So, let's just see what it says here. 22% of the original carbon-14 in a wooden specimen has decayed. Estimate the age of the specimen. So I'm just going to write n. I'm going to look for t now. Okay, let's call it tau. The time, that's tau. I don't know what capital tau is. Probably capital T. So I'm going to estimate n of tau. I know that it's 22% and 0. Am I right? Am I right? Am I right? No, I'm wrong. What's the mistake I made? What should it be? 78%. Yeah? If 22% have disappeared, then there's only 78% of the original quantity. So I should write 0.78 and 0. And that's n0 exponential minus lambda tau. Oh, and lambda, I know it because it's carbon 14. It's, we just computed it, 124 10 to the power minus 4 tau. So n0, I don't need to know it, cancels out from this equation. And I just have one equation for one unknown, tau. So I'll let you find it. With 10 minutes, we can do that. How old is this piece of wood? Yeah, just rewrite the equation, canceling out the n0. What is tau? it's not going to be precise to the year, but probably to the decade or the century. Should be okay. We only kept 3 significant digits. Syntax error. That's not good.
Too fast.
Syntax error. What? You guys better than me. Oh yeah. Okay, I'm going to do it.
You might use my guy. Ooh.
You guys are better than me. Years. So I'm just going to say 2000 because that's what makes sense physically. You can only be certain of 3 digits there. Okay, let's do another. Charcoal specimen found in the Lascaux caves. So that's in the southwest of France. That's where I come from. For 50 or 60 years, it was the oldest proof of human activity, but it's been beaten flat out recently, I think. Can't remember. I must look it up. Assuming that the charcoal came from the people who made the paintings. Huh. That's I'm wrong. Going too fast. In the caves, estimate the age of the paintings. Okay, so I'll let you do that. It's basically the same exercise, except now it's not 22%, it's 85.5%. So instead of 78% remaining, you now have 14.5% remaining. Other than that, it's the same calculation because it's again with carbon. The radiocarbon, okay, is again C14. So if I just redo the same as earlier, I'm going to write that 0. So then I have log. Then tau. One, four, five. Let's see if I can do that one. So I used fractions. Yes. log 0.145 minus 0.24. Yeah, works. How many years do you get for that? 15.6 or so thousand years. Yeah. Older. You can't visit it anymore. They made a copy of it, so you can visit the copy cave. But the cave itself is just protected now. Deteriorating just from the breath of visitors. Okay. So I'm going to stop now.